Hello, Dave Brown again for Teletrain. Today's subject will be reducers. Now, here are some reducers and some reducees. Lovely young ladies in pink. However, this is not the type reducer we're going to talk about today. We're going to talk about speed reducers. And to fully understand this program, you should preface it with our gearing program, because the gearing program will give you the background necessary to understand a number of items we'll be discussing. First of all, what is a speed reducer? Well, it's nothing more than an enclosed series of gears. We're going to cover the most common types of off-the-shelf reducers that you would normally run into. The two types that cover the vast majority of off-the-shelf reducers sold would be right-angle worm and parallel shaft. This is a right-angle worm. The input shaft is here. Power goes in through the worm, then through the worm wheel, and finally to the output shaft. On this unit, every time I turn this shaft 15 times, this shaft turns once. The other basic unit we mentioned is the parallel shaft unit. Now here we have a small gear driving a larger gear. This may be in stages of gearing, such as 1, 2, or 3. The unit we are showing is a two-stage unit. One gear here drives this gear, and we have stage 1. Here is the second stage. We normally call the small gear a pinion. Thus, we have this pinion driving this gear. Now, actually, there's no difference other than size and number of teeth between the pinion and the driven gear. Now, why is a gear reducer necessary at all? Well, basically because most of the power units we have turn too fast to do the job we have for them. Electric motors are the most common source of power in industry today. The most common electric motor is 1750 RPM, or revolutions per minute. An electric motor can be 3500 RPM, 1175, or even 885 RPM. Even slower motors are available, but they are relatively expensive. The point we're trying to make is that although slower motors may be available, it's more economical to obtain speed reduction through a gearing system or through a reducer. Slower speeds are needed on machines such as a cement kiln or an oven conveyor. Here the unit may be required to drive at 1 revolution per minute or even less. As a consequence, we must have some type of speed reducer to get 1750 RPM down to 1 RPM. The basic reducer is composed of 1 or more gear sets. Let's look first at the worm reducer, and as we go through, we can discuss the components. First, we have the input shaft, which goes into a seal. Then there's a bearing to support this end. We also have a bearing on the opposite end. Because of the inherent heat problems with worm units, many manufacturers mount a fan on the shaft extension to help cool the unit. This is the worm. Depending on the particular manufacturer, this worm can either be integral with this shaft or can be keyed onto the shaft. The worm will almost always be hardened steel, which has been ground and polished. Next, we have the worm wheel, which is usually bronze, but with some manufacturers can be cast iron or occasionally some other material. Again, we have a bearing on each side of the worm wheel. One here and one here. Then a seal on each side of the shaft. Let me mention one point here. Usually the bearings on the worm will be ball bearings, since this shaft is turning at high speeds. Roller bearings are usually used on the output shaft, since it is somewhat slower and subject to heavy loadings. This particular unit has 2 output shafts. This is an output shaft, and this is an output shaft. In most operations, there is an output shaft only on one side. Obviously, the input shaft could just as well be over on this side.
Another point I should make, because we do have a sliding action between the worm and the worm wheel, proper lubrication is extremely important with the worm-type reducer. Because of this sliding action, the worm reducer is a relatively inefficient unit, and on high ratios we may lose as much as 30% or more of our input horsepower in the reducer itself. In other words, if we put in 1 horsepower here, we may only get out 2/3 of a horsepower here. The other 1/3 horsepower goes into heat, and in this case the heat is transferred to the oil and in turn to the gear case, which must have enough radiant surface to dissipate the heat. Radiant heat now is what you feel when you step into the sunlight. In some manufacturers' catalogs under performance data, they'll have 2 ratings, a mechanical rating and a thermal rating. The thermal rating tells us at what horsepower the heat is a limiting factor, rather than how strong the gearing or mechanical rating is in the unit. If thermal rating is the limiting factor, we could put a fan so it can blow air directly on the unit. With this fan, frequently we can increase the thermal capacity up to the mechanical rating. If you stop and think about it, a fan blowing air onto a reducer is a pretty good idea. So the manufacturers, in designing these units, decided, okay, why not build a fan directly on the unit? We touched on the fan briefly a moment ago. If you'll notice, as I turn on this end, a fan on the opposite end turns. This is a fan blade, and it circulates air across these vanes, which in turn helps to dissipate the heat from the unit. Many manufacturers install fans on all their larger size units, and most all manufacturers have them available. If you notice, it's on the extension of the input shaft, and this is because the input is always the high-speed side. To return to our original point, this allows more heat to be dissipated from the reducer and, as a consequence, gives a higher thermal rating. The last point we should cover is the housing on the unit. The housing encloses the gear set and is what makes a reducer different from a standard gear set. The material in the housing may be aluminum, steel, ductile iron, or cast iron, depending on the particular manufacturers. For worm-type reducers, the most commonly used materials are cast iron and ductile iron. I'll make a brief point here that's already been covered in a Teletrain's coupling tape. This particular unit we have here would require a coupling to connect it to the motor. The 2 shafts could be connected with any number of couplings, and as I mentioned, a complete discussion of the various coupling types is available on tape. This same ratio and size reducer is also available with a C-face mount. C-face is a term which is used in the motor industry to identify a motor with a machined surface on one end like this. Here is the C-face reducer. This is the input shaft, and this is the output shaft. It is a standard dimension unit and fits a standard C-face motor, as we see here. The units are connected by these 4 bolts, which go into these bolt holes. When the motor and reducer are assembled, we have a complete unit known as a gear motor. This is nothing more than a reducer and motor combined. However, each does have a C-face, which allows interchangeability between units. C-face motors are standard replacement components, and one advantage in the event the motor burned out would be that they can be picked up at any motor supplier. Or if the reducer goes down, you don't have to replace the whole unit. Just replace the C-face reducer section and still use the existing motor. Certain manufacturers furnish a unit already assembled with a special motor. This again is another type of gear motor, but it's still just a motor combined with a reducer. However, in this case, a special motor and or a special reducer are used, and these cannot normally be interchanged between units. Let's discuss bearings in the gear motor. This unit has a bearing here in the motor. It also has a bearing on this end. The reducer has a bearing on each side of the worm, and the worm runs across here. Certain manufacturers produce a unit with a bearing here and no bearing at this point. They depend on the bearing in the motor to be the supporting unit for the reducer. The manufacturer you represent will claim that his way is best, although realistically speaking, there's no pat answer for which is specifically the best way. The pros and cons are that if you have only one bearing in the reducer, you put additional load on the motor bearings, which may shorten their life. Also, the coupling must be able to handle and transmit this load, which in itself is an extremely difficult requirement. If the reducer has two bearings, we get away from the side and in thrust, but then we have the problem of trying to align four bearings. And in actual practice, an approximate alignment is the best that can be done. And normally, a flexible coupling is used to take up the slack. Either style reducer has worked successfully in many applications, although each has encountered problems in certain applications. Let's look at another style worm reducer. We take the same basic reducer we had a moment ago, except we cut a hole through the middle and mount this directly on the shaft we plan to drive. This gives us a unit which looks like the unit shown in this picture and is called a shaft mount. In order to keep this unit from turning over and over when power is applied, we have to bolt it to either a faceplate, and this is a faceplate, or connect a torque arm. A torque arm is a rod which is tied to the floor or anchored to some stationary object to prevent the unit from turning. A torque arm or a faceplate are always necessary on a shaft mount. This, then, is a shaft mount worm reducer. Now, we can combine two worms. We put another worm on this shaft and a worm wheel above it, and we end up with parallel shafts on a double reduction unit, as we see here. We have a worm with a worm wheel underneath, a worm on the backside driving a worm wheel which comes out at this shaft. As you see, when I turn this, we are turning this one. This is a double reduction worm gear. The ratio on a normally stocked single reduction worm reducer will go from 5 to 1 to 60 or 70 to 1, depending on the particular manufacturer. Double reductions go on up to 3,600 to 1 in standard off-the-shelf units. In the double reduction units, this would be two 60 to 1 reductions. A 60 to 1 in the first stage and a 60 to 1 in the second stage. This is a worm, and this is a worm wheel. There are those manufacturers who make a standard off-the-shelf worm unit which has an enveloping worm. Instead of being straight, as you see here, they have a cone-shaped cut down into it, as you see here. While this particular unit and the majority of those on the market do make a single line contact between the worm and the worm wheel, the enveloping type unit has several teeth in contact. As a consequence, it can transmit more horsepower for a given center distance. The term center distance is normally used when stating size in worm-type reducers and means the distance in inches between the center line of the input shaft and the center line of the output shaft. Some advantages of a worm reducer. It's more compact than most other types of reducers for high ratios. For example, we could have a unit this size with a 3,600 to 1 reduction. If we did this with a parallel unit, we would end up with 6 or 8 different stages to get the same reduction. A worm reducer is economical. In fact, one of the most economical reductions available. It's quiet. It can rarely be heard at all. The unit tends to be self-locking. Now, a word of caution, the normal feeling in industry is that anything above about 30 to 1 is self-locking. What we should say is that above a 30-to-1 ratio, worm reducers tend to be self-locking. As you can see, this 20-to-1 will readily backdrive. The reason for the qualification is because if you're in a plant where there's a large amount of vibration, the unit will not be self-locking and frequently will run backwards. So if you have something that must be locked, some additional braking or backstopping mechanism must be used if you're to be sure of keeping the unit from running backwards. If we're going through a worm reducer, since it does tend to be self-locking, a very small brake on the input side will lock the unit. A disadvantage of the worm reducer is that it is inefficient. It's one of the most inefficient reducers available, and as I mentioned, we may in a single stage at high reductions lose as much as 30% or more. It does tend to heat up, since the loss in efficiency goes into the unit in the form of heat, and as a consequence, the unit will run relatively hot. In an area of high ambient temperature, this may be the limiting factor on the capacity of the unit. Ambient temperature means the normal temperature of the surrounding air. One thing which should always be taken into consideration, and this is true of all type reducers of whatever design, you should always use the safety factors which the particular manufacturer recommends. These safety factors could very well be called experience factors, but when properly used, they determine how much capacity we should design for. As an example, we may have a 2-horsepower motor input with a particular reducer. We may design for 4 or even 6 horsepower, depending on what the unit is driving, as well as what the driving force will be. Service factor tables will normally be furnished by each manufacturer, and if these are not followed closely, you're asking for trouble. Most manufacturers design with so much safety factor that worm reducers will often take momentary overloads 3 or more times their design load and show no apparent ill effect. You should remember this very important point. If a continuous overload is applied, it will radically reduce design life. Doubling the load cuts the life to 1/8 of what it would have been. This is to say, if the unit is designed for 25,000 hours, doubling the load will cut this life expectancy to approximately 3,000 hours. Next, we turn to parallel shaft reducers. For the off-the-shelf items of most manufacturers, parallel shafts use helical gearing. We have an input shaft here, which goes through a seal and a bearing. Some manufacturers use a bearing on the other side of the input gear. It's called the input pinion. This gear has a bearing on each side, and the shaft is extended. It goes over into a second stage here, which drives the final output gear. This, by the way, happens to be a 2-stage unit. Every time I turn this 10 times, the shaft will turn 1 time. Again, we have an output bearing and an output seal to hold the oil in the unit. All the gearing is normally polished hardened steel. The bearings are either ball bearings or roller bearings. Ball bearings are most commonly used on the high-speed input and roller bearings on the output. It can, as I mentioned, be 1-stage, 2-stage, or 3-stage. Normal off-the-shelf reduction will go up as high as 300-to-1 on the parallel shaft reducers. The case for the unit is normally made of cast iron, ductile iron, or fabricated steel. Occasionally, it could be aluminum if weight is a particular factor. A lighter type oil can be used for lubrication on this unit since we don't have the sliding action that we had in the worm reducer. This is a C-face motor like we were showing a few moments ago, and as you can see, it's mounted onto a parallel reducer. This is the coupling which connects the motor shaft here to this reducer shaft. The connection on this particular unit is made with a Delron type coupling, and as you can see, we have a closure between the two units. By using this coupling, we now have the motor and the reducer driving as a unit. Here's another style, and it's a built-together gear motor from a different manufacturer. This is a two-stage unit and is essentially the same unit as we had a moment ago. The only difference in this case is this is not a C-face motor, since this is a built-together unit. As you can see, the high-speed pinion is mounted directly on the motor shaft. The unit, by the way, comes as a complete package. You will, of course, have reducers along with standard motors. With the motors and reducers, most manufacturers supply a scoop mount, or what is sometimes called a sugar scoop. Here's a motor mounted on a sugar scoop. The scoop is mounted directly onto the reducer, with the motor sitting out here, and with a coupling in between. Some users prefer the scoop-type mount, and some users prefer one of the other types, but all are quite common. One other type of parallel reducer that is quite common in industry is the parallel shaft mount. Here we have the input. The output has a large hole through it, like the shaft-mounted right angle, and we hang this unit right on the driven shaft. Again, in most units, parallel helical gearing is used. One advantage to this particular unit, we can take a motor mount which looks like this and set a motor directly on top of the unit, as shown in this picture. This gives us a complete unit. This means there is no motor base or anything tied to the floor, except we do have a torque arm or a flange connection to hold the unit and keep it from turning over and over. This type shaft mount has input shafts, seals, bearings, and 1 or 2 steps. These units are normally available in only 3 ratios, 5:1, 15:1, and 25:1. Shaft mounts are normally used with a V-belt drive input, so that by varying the pulley ratios, we can arrive at a number of other different ratios for the total drive. Another factor is the torque arm on the shaft mount. Since the pull of the total unit is dependent on the torque arm, we can put a spring-loaded release mechanism in the torque arm and allow this to be a torque limiting device. This way, if there's an overload, the torque arm would release. The particular advantages of a parallel shaft, either standard type reducer, gear motor, or shaft, as compared to the worm, are first, they're much more efficient. We normally lose something in the range of 1 to 3% per stage, depending on the particular manufacturer and how close the tolerances are on the gears. So on a 3-stage parallel shaft, if we had 1 horsepower input, we get about 95% output. And this 95% compares quite favorably to a worm at, say, 70%. As you can see, there is very little loss in a parallel shaft reducer. And since efficiency loss shows up as heat, there's very little heat buildup, and consequently, it is a cool running unit. Because there are helical gears, noise is not a factor as it might be if we were using spur gears. This unit can be back-driven, and occasionally this is a useful feature. This type drive is called a speed-up drive. In other words, this would be where we wanted the normal input to be the driven shaft rather than the driver. With a speed-up drive, the limiting factor as to how fast you can go is usually the amount of speed the bearing can take on the high-speed side. The chief disadvantage of the unit is that for a given reduction, it is normally a good bit larger than the worm and normally a good bit more in initial cost. Today we've been talking about reducers and gear motors. I'm Dave Brown for Teletrain.